So if you can see, no, excuse me. If you can see this, you can still get a straight line here. But when you're going here, you are getting a curve. So it's advisable that you take where you have a straight line for you to get a better answer. If you take outside, your answer will not be accurate, will not be absolutely correct. Okay, wait. Somebody is typing. You're asking, is it okay to take 0.009 as your strain value for 100? You can take it, but this is just an approximation. If you take 0.009, what do you get? Like I said, your answer 0.009. So you have 100 divided by 0.0009. You get about 111 there. Like I said, the answer is between 100 and about 125. But so if you take that one, it's still okay, because here is more of approximation. You cannot get, that's why it's difficult. If I give you a question like this and all of you get the same answer, then I know you copied, because I don't expect you to take the same value. Your brain cannot work the same way. So yes, it's okay, Sarah. Okay, I can't wait. Somebody is talking here. Let me read this. Where is it? Okay, I can't send to everyone because when I type the answer, I'll click someone. It can't be sent. I don't know why. Maybe my laptop. Okay, that's fine. Thank you. Okay. Yeah, Sarah, that's correct. I think I got that same answer with you. Okay, thank you. All right. So basically, the most important thing here is you know that your Young's modulus is the slope. Is the slope of the straight line. That's all. And that is, so you just make sure you pick within the straight line. But for you to get a better answer, from your 0 to your proportional limit is always the most advisable point. But yes, if you are still within the elastic limit, is good. But it's always advisable that between 0 and proportional limit, where you have a perfect straight line, that is where you should pick. All right, any question before we proceed? Ada soalan, ada masalah. Any question, please?
No, sir, no.
Okay. All right, so again, last week we looked at strain hardening. And we said this is a point where your material moves from elastic limit to plastic deformation. It's a transition between elastic deformation, or no, the use stress is transition between elastic deformation and plastic deformation. Then in strain hardening, your material is trying to resist itself against the applied load. Below the elastic limit, the material behaves elastically. If the stress is removed, then it goes back to its original position. But beyond the elastic limit, your material behaves plastically. That is, your material is in plastic deformation. And in the plastic deformation, as your stress increases, the material tends to strengthen itself. This is strain hardening. Your material tends to strengthen itself against the stress. The more the stress, then more and more stress is needed to produce more deformation, because now the material is trying to resist the force you are applying. So you need more load to produce plastic deformation. So here, this is strain hardening. So strain hardening implies that the material becomes stronger as the strain increases. As you increase your stress on the material becomes stronger, trying to strengthen itself against the load. Now, I want to explain this. Now, when you apply a load to your material, I will draw a stress strain diagram here. This is stress and this is strain. Let's say this is point O. I will take a point here. Let's call this A. Take a point here. Because somebody was asking me a question now, was it Ama or Azaim, that if you pick between 120 and 140, I want to show you the difference. Now, what you will notice is between A and B, this is no more a straight line, it's becoming a curve. Can you observe that? So that's similar to your 120 and 140. Between 0 and A is a perfect straight line. So what this means is this can go up and come down, up and down. Atas, bawa, boyan, boyan. Atas, bawa, goyan, goyan, bole. But now when you come to this point here, you cannot go up and down. Oops, it's gone. Oh dear, wait, did I have another? Oh, I need something to explain. Okay, so I think I just do something and the thing went off. Okay, so you have your stress and you have your strain. So here is point A. This is O, and I have my B here. Okay, so like I was explaining, from your A to B is becoming a curve. Now, if you go up from 0 to A, you can go up and come down. Now, this is this. When you go up here, you come down here. What is your strain value here? Your strain is here. Say your strain is A. That is from here to here is A. Now, if you go up from here, if you go from 0 and you go to B, what is going to be your strain value? Let's see here. Let's say this strain value is B. So if you go from 0, you load up to B. Your total strain on B is, your total strain on this B is B. Now, one thing is this, when you load like this, when you want to unload, your unloading must follow the same pattern as your loading in this line. So for example, at B, if you want to unload at B, you do a line that is parallel to this one here. So this line must be parallel to this line. So if you unload at B, you get C here. This is C. What does this imply? If you load from here to here, your total strain is B. But when you unload, you cannot get back everything. When you remove the load, because already you are in plastic deformation, when you remove the load, you can get back some, but you cannot get everything back. So in this case now, you can recover from here to here, you get back, but from here to here, you cannot get back. Let me explain this using a mobile phone, okay? Now, you decide to go to Cellcom store in Maiden. You want to buy iPhone 12. How much is iPhone 12 approximately? iPhone 12. I want response, please. Quick.
17,000 17,000.
17. Okay, let's go for iPhone 10 then. That's too much. I don't want too much. iPhone 10. Let's go for iPhone 10. iPhone 10.
2000.
5.
Apa?
5,000.
Okay, so RM 5,000 ringgit. All right, now you go to shop now. Today is 7th of April 2021. You go to the shop, you get your iPhone 10 for 5,000 ringgit. Now, you want to sell your iPhone 10 on Friday. How much are you going to sell for? If you want to sell, you unbox it, you open it, you use it now from today to Friday, and you decide you want to sell back your iPhone 10. How much are you going to sell it for?
4,500.
700.
Okay, so now you are going to sell for 4,500. What happened here? You've lost 500. You recover back, you pay 5,000, you can only recover back 4,500. 500 is lost. The same thing applies here. You pay from here to here is your 5,000. So from here to here is your 5,000. From here to here is your 4,500. From here to here is lost, cannot get back. So what does that mean? You have what we call the elastic recoverable, which is what you recover back. No, this is your recoverable. You recover back this from 0 to C is recovered. From C to B is lost. Then you have your permanent deformation. Your permanent strain is what you lose here. This one is gone. Here, 500. Limaratus already gone. You cannot get back. So in this case, the same thing apply here. Here, gone. Cannot get back. But from here to here, you can get back. So that is the same analogy. When you unload your material beyond your elastic limit, then you are going to lose some strain. Some will be lost, some will be regained. You regain some, you lose some. Okay, let's explain from your lecture note. Okay, strain in a stress strain diagram can be described in two ways. You have what we call the recoverable elastic strain, you get back. And you have the permanent plastic strain, cannot get back. Recoverable can get back. Can get back. Permanent cannot. So your recoverable elastic strain is a temporary strain on the material that can be recovered after the strain is removed. So you get back that one. Whereas for your permanent elastic strain is the permanent strain on the material that cannot be recovered after the stress is removed. Now, a good example is this. Now, if you load this from 0 to A, you discover this is where your straight line stops. From here now is bent. So if you load this, that means you have load beyond your elastic limit. Your elastic limit should be somewhere here. Now, if you unload this, this is what you're going to get. So for example, if from here to here is C, from here to here is A, and from here to here is B, your total strain at A is C from here to here. When you unload back, your strain, when you unload your strain at B will be A. This implies that you are getting some back. You get back this one, and this one is your total loss. So your B, you recover because this one is get back. This one cannot get back. This is the one that is totally lost because you are still going to have this permanent deformation on your material. Instead of going to 0, it's coming here. So the total deformation of your material is this, but this one you get back. So what you have here, for example, if you load a material above the yield point to A and then unloading to point B, then your total strain is C. Now, the total strain on the material is C. The recoverable elastic strain is B because here, when you unload back, you get this, you recover this, you lose this because this is going to be the total strain that is going to be left on your material now. So your recoverable is B and the permanent is A. So you recover some, you lose some. And for you to determine your recoverable is just your stress divided by your Young's modulus. Right, so any question with that one before we move to strain energy?
No, sir.
Okay, so very quickly, I'll be looking at strain energy. Strain energy. What is strain energy? Strain energy is the energy that is internally stored throughout the volume of a material deformed by external load. When you apply a load on a material, the energy that is inside the material to resist the load is what we call strain energy. And strain energy can be obtained from your stress strain diagram. So for example, this is my stress and strain, and it goes up like this, or probably, okay. Now, if I want to, I can determine the strain energy of this diagram. And for me to do this, there are two ways in which we can do it. You can either express it in terms of modulus of resilience or modulus of toughness. What is the difference between the two? I'll be explaining the difference between the two in this class. Modulus of toughness or modulus of resilience. But one thing you need to remember is the unit for your strain energy is always joules per meter cube. So when we ask you to calculate the modulus of resilience, your final answer, your unit must be joules per meter cube. And if we ask you to calculate the modulus of toughness, your final answer must be unit must be joules per meter cube. Now, how do we arrive at joules per meter cube? Let's look at this. Your stress is either in Pascal or MPa. Let's say this is MPa. This one is no unit, and you have this. Now, because we are talking about energy, your energy is in joules. So what we need to do is we need to change this your Pascal to joules. Let's just use Pascal here to make it easier. We need to change your Pascal to joules. Now, you remember that force is equal to work done. Force is equal to work done multiplied by what? What's force? Okay, what's the formula for work done? Work done
FS.
is equal to what? Force
Times distance.
times distance. Okay. Now, your work done is in joules, your force is in Newton, and your distance is in meter. Is that correct?
Yes.
Yes.
Check.
Yes, sir.
Pascal is equal to what? Newton all over meter squared.
Meter square.
Then if you make this the your Newton here will be what? Pascal multiplied by meter squared. Is that correct? From here,
Yes,
N
yes.
is equal to this multiplied by this. Now substitute
Yes.
for N here. Substitute this into here. Then you have your J to be equal to what? Pascal multiplied by meter squared, which is this one. Then times meter. So from here now, your J will be Pascal multiplied by meter cube. So from there, your J equals Pascal multiplied by meter cube from this one. Meter squared multiplied by meter. Then now make Pascal the subject. Your Pascal is going to be joules all over meter cube. So this is where we got your joules per meter cube. That is a unit for your strain energy, which is your modulus of resilience and modulus of toughness. Is everybody okay with this? Hello? Are you okay with this?
Okay.
A bit blur, sir.
Okay, then I start again. Wait. I start again. We have Pascal. And we say Pascal is Newton per meter squared. That's correct, right? Hello?
Yes, sir.
Okay. Then we said work done. Work done is equal to force times distance. And your work done is in joules. The unit for work done is joules. The unit for force is Newton. And the unit for distance is meter. Okay? Then we can now make your J. If you make N the subject here, make N the subject here, your N will be equal to, which is your Newton, will be joules all over meter. Is that correct?
Yes, sir.
Okay. Now, let's now come back here. Your Pascal is equal to N all over meter square. Your N is what here? Let's substitute this. Your N is J all over M. That is this one, N. Then times 1 all over M squared. So from here, your Pascal is equal to J all over M times M squared, M3. Finish. What we want to do is we are looking for relationship between Pascal and joules. Hello?
Hello.
Yes, sir. Ah, got you, sir.
Check up.
I understand. Hello.
All right, so
Hello.
like I said, the unit is joules per meter cube. So what I'm going to look at now is I'm going to look at the difference between modulus of resilience and modulus of toughness. Like I said, I repeat myself, your strain energy can be expressed in terms of two ways. One, modulus of resilience and modulus of toughness. Now, what is the difference between these two methods? The difference is this. You can have this. And you can have this. What is it? This is A and this is B. What's the difference between A and B?
A is
What is
brittle material.
A is brittle material that is only elastic deformation, and B is plastic deformation, which is ductile. Thank you. Now, for you to calculate your strain energy, all you need to do is you calculate the area under the graph. For example, you just close this up now. You calculate the area under this graph. Then if it is for ductile material, you under the graph. The strain energy for this is area under the graph, and this one area under the graph. So what's different between the two? This one is modulus of resilience. That is only the elastic limit up to the elastic point. No strain hardening. And this one is modulus of toughness. That's the difference between the two. But all you need to do is you just calculate the area under the graph. All right, so let's look at this. So modulus of resilience is the ability of material to absorb energy without any permanent deformation. That is within elastic limit, no permanent deformation. This can simply be expressed as the area. Now look at that. Area under the curve within the elastic region. So here, from here to here is your elastic region. So you just calculate the area under this graph. Now, what type of shape is this? What type of shape is this?
Triangle.
Okay, so this is a triangle. So then what is the area of a triangle? Area will be what? Area of a triangle.
Half times length and height.
Half base times height. From here, what is your base?
Straight.
Epsilon y. What is your height?
Stress.
So the area here now is half epsilon y multiplied by your U stress. So this is for modulus of resilience. Then you can change your E. Your epsilon, you said your stress is equal to E epsilon. So this is Y. So from here now, your epsilon Y will be equal to what? Stress Y all over E. You substitute that here, then you have half multiplied by epsilon Y is stress Y all over E multiplied by stress Y. That is your stress Y squared divided by E. So you can either use this formula or this for your modulus of resilience. So if we ask you to calculate modulus of resilience, just use this formula, finish. Or if you cannot remember the formula, just remember that it's just the area under this triangle here. You just calculate the area of this triangle, finish. All right, so from the figure, the area under the graph is equal to the area of a triangle. That's what we've done already. And we said it's half base times height. You have half this multiplied by this. This is this here. And if you substitute for epsilon y, then you have sigma y all over E. So then the area of your modulus of resilience, now for modulus of resilience, we are using UR. Your modulus of resilience is this one here. It's either half sigma y multiplied by epsilon y, which is the same thing as half sigma y squared all over E. So if you know your U stress and you know your Young's modulus, you can calculate the modulus of resilience. And if you know your U stress and you know your strain at yield, you can calculate your modulus of resilience, depending on what you are given. Any question with modulus of resilience, please?
No, sir.
No, sir.
Then for modulus of toughness, like I said again, is the total area under the graph. Okay, but before we look at modulus of toughness, you said there is no question. Let's look at this problem. Let's look at this and solve this. The stress strain diagram for my steel sample is shown below. Determine the modulus of resilience of the material. So they want you to calculate the modulus of resilience of this material, and they are telling you that your yield point is here. So from here to here, this is within the elastic domain. So assume it's a triangle. So now I want you to calculate the modulus of resilience of this. So which formula are you going to use? We have two formulas. Which one are you going to use? You have this one and this one. Which formula? Pardon? Which formula are you going to use?
The left one, 1/2 times stress times strain.
Okay, so now let's do that. So somebody said, oh, I don't know who's talking. I didn't see that person. He said use 1/2 stress y darab epsilon y. Okay, so let's do that and type your answer, then we continue. I just want to make sure that you are following the class, please. And if you have any problem, then you complain. I will answer your complaint here. Let's do that very quickly. Okay, somebody is typing to me, but this is private. Maybe I copy this and send to everyone. Somebody send me private message. Maybe I mention her name. She will know who the person is. Somebody send me this one. It said it's 1/2 times 200 multiplied by 0.0032. And that is Nosara. Thank you. I want the others to do theirs. 0.34. Okay. Thank you, Diane. Yeah, now I can see my friends coming up. Before now, they've been quiet. 3532, Aquila, Cairo, Fadley. Thank you. Thank you. Oops, oops, oops. They are now getting fast. Who has this 5? Azaim, how do you get 5 times 10 raised to power minus 5? Azaim, that one is confusing.
Sorry.
Okay, the better that because that one is wrong. Okay,
Wrong.
thank you. Thank you. Yeah, okay, okay. Okay, thank you, guys. Thank you. So I just continue. All right. Now, because of the point you are picking here, our answer is slightly different, but that is okay. So don't worry. So for me, I'm picking 0.0033. It may not be totally true. I think 32 is more better. So for those that pick 32 are even more better. Okay. No, I think 33. Wait, this is 5. I think between 33 and 32. But all you need to do is you multiply, just calculate the area under this curve, the area of the triangle, which is half, base, which is here. Oh, where is it? The base is here, multiplied by your height. Finish. So easy, eh? So any problem, please, Ada Sualan. Tuan, Ada Sualan.
Tak ada, sir. Untuk
Okay.
sekarang.
Okay, thank you.
No,
Okay,
sir.
so
No,
very
sir.
quickly, let's look at modulus of toughness. Modulus of toughness. Like I said to you, for brick 2, modulus of resilience, whereas modulus is for. So then, if I have this material like this, how do I determine what type of shape is this, please? Because like I said, it's the total area under the graph. So you need to calculate this total area. What type of shape is this? This shape is what? What shape is this one here? Hello? Trapezium. Okay. Aquila said it's trapezium. For me, I don't even know the shape anyway. So for me, this has no well-defined shape. And because it has no well-defined shape, what I always advise is you divide this to shape that is suitable. For example, if I decide to cut this here, and I decide to cut this here, and I do something like this. Okay. I can take this to be triangle. This is what? 2 is what? Then this is another shape here, and this is another shape here, 4. So my 1 is triangle, my 2 is a rectangle, my 3 and 4, I can assume they are triangle. because I can just do this like this. This is an approximation, so it's more like a triangle. And from here, I can determine my area. I'll just do the total area, which is my modulus of toughness, is area 1 plus area 2 plus area 3 plus area 4. For area 1, it's going to be half base times height, plus area 2, that is going to be length times breadth, plus area 3, half base times height, plus area 4, half base times height. Finish. Then I calculate, I get my answer. So for modulus of toughness, is the ability of your material to absorb energy with large strain hardening. That is permanent damage. And this can simply be expressed at the end. The total area under your stress strain curve. Toughness is UT. And like I said, because the shape is not well defined, then you need to divide it into a solvable area. So if you look from this figure, the area under the graph does not have a well-defined shape. Like I said, somebody was saying it's trapezium, okay? But the shape is not well defined. So we are better off to define it to a smaller, what's it called, a simpler shape that we can understand. So now if you look at this, I've divided this into 1, 2, 3, and 4. My 1 is triangle, 2 is triangle, 3 triangle, and 4 is rectangle. So for me to now do this, I just have to calculate the total area of the shape. So divide the curve into different segments with a well-defined shape. Then calculate the area of each shape and sum together. But remember, you are only using this to get the value. Your final answer is in joules per meter cube. Because over time, if my student calculate the area, they just put meter squared. You know the formula for area is meter squared. You're only using the area to get the total value of all the energy stored in this area using that approach. But your final unit is still joules per meter cube. Faham ta faham? Hello?
Paham, sir.
Okay. Okay. Ada soalan. So if there's no question, let's look at this example.
No, sir.
Okay, so let's look at this example. You have the stress strain diagram for my steel tensile sample shown below. Determine the modulus of toughness of the material. So here, everything here, you calculate the total area here. So like I said, I want you to divide it into 4. So 1, 2, 3, and 4. And calculate the total area on this curve. So let's do that very quickly. So compute your modulus of toughness for this material. Compute your modulus of toughness for this material. So while you do that, let's take one minute off. students are so fast, eh? All right. Thank you, Mohammed Shafiq. Shafiq is 1.5775. Thank you, Fazan. Okay, Mohammed Azaim, 1.38. Okay, so let's wait for others. Others, we are waiting for you, please. I've not seen any of my ladies there. So let's wait for the ladies to come online. So we are waiting for others. Azahim, who is there again? Okay, still the same set of people. So we are still waiting for the other people. Where is Diane, Sarah, Kairon, City Masba? Oh, great. So all of them are coming now. Who is this? Logan is 1.2. Logan, yours is very far. Eh? Zarif 1.42. That's better. Logan is very far. Now, like I said earlier, I don't expect your answers to be same. Okay, because I expect you to I expect everybody to pick different locations. Okay, who is this? Afik, thank you. Afika, I know, thank you. Oh, Diane is still calculating, thank you. Varatan, okay, that's Logan, okay. Who is this? Mohammed Afik Daniel, okay, thank you. Kairun Fazli, thank you. Taju, thank you. Mohammed Ami bin Ibrahim, yours is a bit far. You are too far off from the others. You should be more closer to others than far away. No, Aquila, thank you. Yeah, I want us to finish that so we can continue. Nuru Kodria, thank you. Mohammed Amiru Amin, thank you. Terimakase, c'est moi. Afnan Terimakase. Shahid Amil, Shahidan Terimakase. Yeah, I'm waiting for those that are still calculating. So I make sure that at least we are together. Who is this 1.3? Nofara, thank you. Bisvan, No Athika, Mohammed Amil, Mohammed Amin, okay, yeah. Natria Fatira, Nuru Shuhaida, Moses, Bastria. Okay. Where is Sarah? Sarah, the moment I know your name in my class, I'll be asking you for questions. Where is Sarah? Oh, thank you. She's just waiting for me to mention her name, then she will respond. Akimi, your unit is megajoules per meter cube. Megajoules per meter cube. Sarah, why are you confused? What's the problem? Check up.
I thought the second segment and the third segment, we can assume it as a semicircle, but I
Okay, you
calculate
took it as
is
semicircle. Okay. Yeah, you can take it as semicircle, but to make life easy for you, just assume it's a triangle. Your answer
okay,
cannot be absolutely perfect, but at least you'll be close.
Okay, sir, thank you.
Yeah, you can just assume it's a triangle because if you look at that shape, It's not totally far away from triangle. It's just going to be a little difference. Because this is not totally semicircle. If you look at this, you have this. But semicircle should be like this. So it's not a total semicircle. So it's better you just assume, Diane, thank you. All right, so let's just continue. So it's better you assume to be a triangle. But like I said, it's not absolutely correct. Okay, but
Sir,
if you get closer, yes, please go on.
can I combine 1 and 4 to make trapezium?
One,
Because the 1 is triangle and 2 is square, right? When we combine, we get trapezium.
okay, you want to combine 1 and 4. Okay, that's good for you. For why I made it easier is if I ask you what's the formula for area of a triangle, you know it easily. If I ask you what is the formula for area of a rectangle, you know it. But if I ask now what is the area of a trapezium, many people may not know. Do you understand?
I understand.
So
Thank you.
because to now make it easy, that's why we choose something that is easier for everybody to relate with. We can get this shape and say, okay, this shape is trapezium and we are going to use trapezium formula to calculate it. But if I ask you to calculate, say for example, I give you in an exam and you don't know the area for trapezium, then what do? You are confused, you cannot solve. But if you know that you can divide this into smaller shape and you know the area, this is triangle, this is triangle, this is rectangle, then you can easily solve. So that's why I've made it so easy. Yes, you can even use the area for trapezium to solve the whole thing. If you use the area for trapezium, your answer will be close to what you have. Just assume this is a trapezium and calculate. Your answer will be close. But what happens if you're in an exam situation and you don't know the formula for area of trapezium and you cannot find it anywhere? Do you understand my point? Hello?
Yes.
Okay, so that is why I decided to use something that everybody will easily remember. Most people here will remember the area of a triangle and the area of a rectangle.
Sir, understood.
Okay, thank you. All right, so let's proceed, guys. Thank you guys for, so like I said, for me, it's easier to divide it into solvable area. And what I've done is I've divided it into 4 areas, 1, 2, 3, 4. 1, 2, 3 are triangle, 4 is a rectangle. And I calculate the area of triangle 1, 2, and 3, and area of rectangle, then I add together. This tambani equals to my modulus of toughness. And like I mentioned earlier, your unit is not meters squared, your unit is joules per meter cube. You will see here joules per meter cube. So if this is megajoules. If it is kilojoules. If it is is gigajoules, depending on what you have here. So any question with this?
Sir.
All right, so if there's no question, I think our time is fast spent. Let's quickly look at Poisson ratio. Now, I have this thing last week I showed you. I showed you this last week. I have 2 samples here. Now, this is tested. This is untested. Now, one thing we discover when you test this sample, your height, the height here will increase. And your width here will decrease. Say, for example, if you have this, if you can see from there, you will discover that the width decrease and your height increase. So what does that mean? When you apply a load on any sample, there is always going to be deformation on both your axial direction and your lateral direction. So if your axial is increasing, say for example, your length is increasing, your diameter will be decreasing. If your length is decreasing, your diameter will increase. It's directly proportional or inversely proportional. If this increase, this will decrease. So then, because your height is decreasing, or your height is increasing, height, h, or let's use L, your length increase and your diameter decrease. Then we want to see what is the ratio of the increase in your length to the decrease in your diameter. And this ratio is called Poisson ratio. We want to see the ratio of the increase in your length to decrease in your diameter, or the ratio of increase in your diameter to decrease in length, depending on the application of load. If you're applying tensile, your length will increase, your diameter will reduce. If you're applying compression, your length will reduce, your diameter will increase. So when a deformable body is subjected to axial force, not only does it elongate, it contracts laterally. That means it increases in size, in length, it reduces in diameter. So the ratio of your lateral strain to your axial strain is called Poisson ratio. Poisson ratio. So what, say for example, now let's see this. Let's just draw something here. Quickly, I draw this. I pull here. And after pulling, I have this. Okay, so this is my original length. This is my final length. Now, say for example, this length is 10. What will be from here to here? Just give me value.
10.1.
Pardon? This is from here to here is 10. From here to here. Cannot be 10.1 la. About 12.
12.
Okay. Now, let's say from here to here, this is 5. What will be from here to here?
Maybe 4.
Okay, 4. Maybe 3. 4. Okay. Now, you want to calculate your delta L. Your delta L will be what? L final minus L original, which is what? 12 minus 10. And that will give you what? What's going to be your delta L? That's 2. Okay. Now, let's calculate your delta D. Delta D is your D final minus D original, which is 4 minus 5. And what's your answer? Look, it's not 1, but minus 1. Thank you. So it's minus 1. Now, we want to calculate your average or your ratio. We said your ratio of this all over this. So you have lateral strain. So your Poisson ratio is lateral strain. Now you need to change to strain all over axial strain. Your axial is a function of length. Your lateral is a function of diameter. Now this diameter is going to give you minus divided by plus. Your answer is going to be minus. So for your answer not to be minus, because you want your Poisson ratio to be positive, for your answer not to be minus, then we introduce a minus here. So this will turn your answer to become positive. Is that okay? And your strain, like we said before, strain is change in length all over original length. that is in your axial direction. Then your strain in lateral direction is changing diameter. So if you substitute this equation of Poisson ratio, then you're going to have your Poisson. This is your strain in X, and this is strain in Y. And like I said, because your strain in X is going to be negative, you introduce a negative sign here to make your answer positive. Any question, please? Ada soalan?
No, sir.
Okay, let's look at this problem here. You have a specimen. The original length, L original, is equal to 50 mm. Diameter original is 10 mm. Then you apply axial load. Your delta L elongate to contract delta D 0.15 mm. So they want you to calculate the Poisson ratio. So can you calculate the Poisson ratio, please? Poisson ratio is minus delta D all over D naught divided by delta L all over L naught. Finish. That's easy. Thank you, Moses. Thank you, Zarif. These students are so fast in Shafiq. Thank you. Let's wait for others. Megat, Afik, I know. Thank you. Thank you. Thank you. No Fatim.
Sir,
Yes, please continue. Check up.
delta D no negative, positive.
Pardon me?
Delta D itu the negative or positive 0.15.
If it's contracting, it's going to be negative.
All right.
Contract is negative, elongate is positive. Contract is reduced.
Put negative 0.15.
Yes, please. All right, thank you, Sarah. Thank you, Shraida. Navendran. Right, thank you, guys. Thank you very much. So all you need to do is just substitute in your values. Okay, so you just substitute in the values. Like I said, for your delta D, because it contracts, that means it's reduced, it's negative. Elongate is positive. Okay, so any question with that before we proceed? Ada soalan, ada masalah. Ada soalan, ada masalah.
Tak ada.
Tak ada. Semua baik, eh? Okay, so the last thing I'll be looking at is, I'll be looking at your shear stress, shear strain diagram. If you have a shear stress, shear strain diagram, how do you correlate or how do you determine the material properties? Right, so shear stress, shear strain diagram. The shear stress shear strain diagram is similar to the shear to the strain. Before now, we've been looking at this strain. This is normal stress, this is normal strain. And then you have this. Now, what we are looking at now is this. Rather than having normal stress, we change this to shear stress, tau, and rather than having normal strain, we change this to gamma, which is shear strain. Then you have the same curve like this. So like I said, it's similar to your normal stress, normal strain diagram. For your normal stress strain diagram, you use normal stress and normal strain obtained from tensile test. Now you need to note this. For this is from tensile test. For this is from torsion test. While for shear stress, shear strain diagram, the use of shear stress and shear strain obtained from torsion test is used. So the only difference between them is for this one, you do tensile test, you get your data, you can plot it. Whereas for this one, you have to do torsion test. You cannot get shear stress, shear strain on tensile test. You get it from torsion test. Though you can convert from normal stress to shear stress using some approximation, but you cannot get shear stress, shear strain from tensile. You need to do a torsion test. Now, one of the most important tests to be carried out in order to obtain your shear stress, shear strain diagram is the torsion test. During the test, you're going to be applying torque on the sample. So rather than applying load and you calculate the formation, in this case, you apply torque, then you get angle of twist. As you apply your torque, twisting, your torque is like you are twisting the member. As you twist the member, then you begin to get angle of twist. Where is this one that I used last time? So it's just like you are twisting the member. So as you twist the member, then there's going to be the angle of twist. So here now you are not getting elongation or contraction, you are getting angle of twist. And that's why you are going to have a change in angle. Okay, so during the test, the apply torque on the sample and its corresponding angle of twist. So here you apply torque, then you get angle of twist. It's recorded. Then you will now change your torque. You change this to shear stress, and you change your angle of twist to shear strain, like we did for the other one, shear strain. And for you to change it, okay, so the measured torque can be converted to shear stress. So your stress, your shear stress is your torque multiplied by your radius divided by your polar moment of inertia. And your shear strain, gamma, is equal to your C, which is your radius, multiplied by your angle of twist divided by your length. So the measured angle of twist can be converted to shear strain using C multiplied by your angle of twist. Your C is radius, and this is your angle of twist, and this is your length. So you have radius multiplied by angle of twist by length. So during experiment, what you will be recording is your torque and your angle of twist. But before the experiment, your instructor will ask you to measure your radius. You measure the radius, then you measure your length. So if you know you measure this, and you make this one you take from experiment, then you can calculate this. And for J, your J is a function of your radius of the sample. So if you know your radius, then you can calculate J. I'll be teaching you that in your class. But if you know your radius, you can calculate J. So here now, if you know J, then you can calculate your stress. And once you have your shear stress and shear strain calculated, then you can plot your graph like we did for normal stress, normal strain diagram. Is an example of your shear stress, shear strain diagram. Again, on this graph, you have your yield, you have your fracture, and you have your UTS. So this is the maximum, this is the last point, and this is where it's changing from elastic to plastic deformation. I think there is a way to convert from sigma y to tau y. I think there's a multiplication factor. So if you have this one, then you can just determine from this graph, and this place here, the slope here, instead of E, is going to be G. And your G is your shear modulus or modulus of rigidity. Shear modulus or modulus of rigidity. And your G is equal to this all over so it's just changing from E to G. There's changing from normal stress to shear stress and normal strain to shear strain. Finish. Okay, similar to conventional stress strain diagram, below the yield, the material obeys Hooke's law and deform elastically. That is, your shear stress is proportional to your shear strain. And the constant of your proportionality is G, which I called modulus of rigidity or shear modulus. So from the graph, G represents the slope of the straight line, like we did here. The slope here of this is your G. Okay. Now, again, like I said, you can relate the properties of your shear stress, shear strain diagram to normal stress, normal strain diagram. For example, your modulus of rigidity, which is your G, can be related to your modulus of elasticity and your Poisson ratio. So if you have your G, if you know your E and you know your Poisson ratio, you can calculate your G because your G is equal to E divided into 1 plus Poisson ratio. And if you know your G and you know your Poisson ratio, you can calculate E. If you know your G and your E, you can calculate your Poisson ratio. So you can actually relate them together. Any question, please? Ada Soalan.
No question.
So you can differentiate between the stress strain diagram and shear stress, shear strain diagram. You can differentiate between modulus of rigidity and modulus of elasticity. You can differentiate between modulus of resilience and modulus of toughness. These are things you need to be able to identify because they can be quite confusing, but you need to be able to differentiate between them. Okay, so if there's no question, let's look at this attendance. Right, so if there's no question, I think that's where I'm going to stop for today. So just today, we've looked at a few things. We will recap on what we did last week. Then we looked at strain energy, Poisson ratio, shear stress, and shear strain diagram. Shear stress and shear strain diagram. So if you have any question, please, you can ask before we close. But in the absence of nothing for now, I'll stop sharing so we can take attendance. Okay. Amiru Wafi.